Mr. Wizard. That's what all the kids in the neighborhood call him because he shows them the magic and mystery of science in everyday living.
Hi, Mr. Wizard.
Oh, hi, Bobby.
Say, that looks fun.
Watch.
What is it?
Well, I'll watch for a minute.
That's great.
Don't you get any idea what that is?
No.
Really? Well, over here, I'll give you a different kind of clue. That has nothing to do with these balls, it looks like, but really has a lot to do with it. Come over here, I'll show you. See this tall tube here? Yeah?
Mm-hmm. Just a glass tube with some wires running out.
Okay, now I'm going to throw that switch. They give you any idea as to what those balls are all about?
Those balls supposed to be the spark?
Well, what is it that's causing the spark?
Well, electricity.
That's right. And that's what those balls represent, electricity.
Really?
Yeah, well, you'll understand that a little more in a minute. First, before we investigate that, I want you to tell me about electricity. I assume you realize it's important, but just how important is electricity to everybody?
Well, it's very important. I mean, it runs the vacuum cleaners and practically runs the house. I mean, the TV and the radio and heating pad and...
How about industry, too?
Oh, it's very useful there.
You use it to run all kinds of motors and things, but how about you personally? How do you use it?
Oh, sure, I use it a lot, and especially my electric trains
Yeah.
run that, and the heating pad, my TV and radio.
Right. So, you use electricity quite a bit, therefore, seems to me it's logical that you ought to know something about it. What is it, anyway?
Well, something to do with electrons, isn't it? I mean, I read something like that. Electrons, electricity.
Oh, you mean the electron, the word electron is where we get electricity?
I think so. I'm not sure.
That's pretty good. I think you know more than most people would know about electricity. Actually, they use it every day without realizing what it's all about. So let's start from the very beginning now. What is an electron?
Well, I don't know.
Well, come on over here and let's take a look at these balls now and see if we can make some sense out of it. First place, this little circle right here represents an atom. You know what an atom is?
Well, an atom's well, I don't know, it's something that's got a nucleus in the center and a proton and a neutron or something like that.
Well, at least you've got some of the terms. You're a little inaccurate, though. Here's what an atom is. An atom, first of all, to define it, is the smallest piece of anything that maintains the characteristics of the original piece. In other words, molecules, you know, are made up of atoms. And the atom now, let us say that this atom is an atom of copper. See? And a copper wire that this thing represents is made up of many of these atoms. That atom of copper is made up of a nucleus, this thing in the center, and electrons, many more than this, that are spinning around the outside. Now, the electrons now are the thing we're interested in, right? You mentioned them, didn't you? Well, an electron now is a tiny piece of electricity. It has a negative charge, and they're spinning around the outside here. Now, some of these electrons in copper are free to move around a little bit. They're not held here next to this nucleus as tight as some of the others. So if we take another electron from someplace, see, and bring it up here and get it started in the wire, these two electrons, being of the same negative charge, repel each other. So if we can force an electron down here like this, we can get one of those free electrons to move away. See?
Oh, and then I do the same thing to the next one.
Okay.
That got close.
That one pushes over
away.
here and gets this one away. Until finally, as we have this whole long line of atoms inside a copper wire, we can get the electrons to flow from one atom to the other, just like this. See?
Hey, that's something.
Now, do you know what electricity is? What?
Well, electricity is the flow
Of electrons. Right, through a wire here. Okay. Now, when it came down here, notice that I had it hit this little piece of tin, see, and make this bell ring. Well, what this represents is when the electron moves through the wire, it finally comes to an obstacle or a change. It's different than the wire. We can now get it to do useful work because it has energy. In this case, it dropped off here, pushed a switch, and rang a bell, you see.
Oh.
Just like when you push the doorbell. Okay, now after it's done this work, we got to do something with these electrons. So they run back here
Oh, I see.
and went right back where we started from.
That's something.
So this is a whole circuit. Copper wire going out to a bell, coming back. Now, what is it that makes this ball roll down that way?
Well, gravity pulls it down.
Right, gravity is pulling it down this way. See? So in order to get the ball to roll, I have to pick it up from the source down here, up, and get it started. and now gravity takes over. See, it's back down here where we started. However, what kind of force am I using to overcome the force of gravity to pick up that ball from the tin can and put it up this high?
Well, I mean your muscles.
My muscles, that's right. So really, I'm using the energy from my muscles to ring that bell down there. Right?
Right.
Because I'm taking this, giving the ball energy. When I let go, gravity now pulls it down, so I'm using a combination of gravity and my muscles to ring that bell. Okay. Now, in real electricity, while these are little balls, you know, and gravity is helping us, what are the force that we use to take an electron from someplace and push it into the wire? You know?
Well, not really. I read something. There's a big power plant near Niagara Falls. You know, when the water comes over that thing, it comes down, boom. Doesn't that falling water, I guess, would be?
Well, now, you're partly right, but you don't just go stick the copper wire in the falling water and get electrons rushing through it. It's a little more complicated than that. So let's see now if we can find out some of the principles that scientists have developed. They push electrons through the wire. In order to do that, we go over here to a piece of metal. Here. See, this piece of metal.
Piece of metal.
Yeah, this looks like an ordinary piece of metal. However, if you take that piece of metal and put it down here and touch it to the nail, I think you'll find that it's not just an ordinary piece of metal. See?
Oh, it's a magnet.
That's right. It's a magnet. So now we know that there is a force of some kind holding up this nail, don't we? Let's see if we can't get a better look at that force by making it visible a little better than with the nail. Here, let's take the nails out of the way. Put the magnet underneath here like this. See? Now, see what this is?
Iron metal filings.
In other words, these are little tiny pieces of a nail, in effect.
Oh.
See, little pieces of iron. So they're going to be attracted to the magnet just like the nail was.
Oh, you can see the outline of the magnet
And
underneath.
here's the other end up here. Now let me tap it a little bit. There. Now we're beginning to see the lines of force that ordinarily are invisible. In fact, you can see them. They go around here, see?
Oh, they go in one end and out the other.
Yeah. Now, so I want you to realize that there is a whole area right here where the invisible lines of magnetic force exist. See? Right in the end of this magnet. So what I want you to do now is I'm going to pick this up and I want you to take the end of that magnet and hold it out. See? Because what I want you to do is to put it near this coil. But before you do that, I want you to notice the coil here. See, here's wires going around here. Wires come out, go over to here, and go into the back of this meter. So whenever we get the needle of this meter to move, we know that we have electrons flowing through this wire. Okay? Now, you take the end of this magnet that has the invisible lines of magnetic force going through it, and put it here through that hole in the coil.
Hey, the meter jumped.
See how the needle moved, eh?
When I move it, hey, it moves the little needle.
Sure. So this means now what?
Oh, that we have electricity.
Right. We have forced electrons from the free electrons that were in this wire, in this copper wire. We've forced them now to move through over here and make the needle move. Now, what did you use to do that with?
Well, the magnet.
Right, the magnet. Oh, but now try something else. Put it in here. Now, the needle moved. But now, is it moving now?
No.
Now, move it just a little bit.
It moves when I move, but when I stop, it stops.
Yes. So there must be some other force other than the force of magnetism, because here you now have a magnetic force right there, invisible lines of force going through here.
Well, am I doing it?
It must have something to do with your movement, right?
My muscle, yeah, I'd be moving it.
In other words, in order to make electricity using a coil of wire and a magnet, you must use movement. In other words, a combination of your muscular force moving here, plus the lines of magnetic force in the magnet. In other words, the scientific principle, as the scientists outline it, is this. Whenever you have a magnetic field, if you will cut this magnetic field with wire, like this, you will have a flow of electrons in the wire. Now, you hold the magnet still, because I'm going to move the coil and see if the needle moves.
It
Does the needle move? Notice when I stop,
it stops.
when I move.
It moves.
Okay.
Oh, so you can either move the coil or the magnet,
Right,
the same
coil
thing.
or the magnet. So we can now get a bunch of electrons to move in a wire. We'll push them away using magnetism, moving magnetism. Right?
Right.
Okay. Now, what are the three important parts?
Well, the magnet.
Yeah.
And the coil of wire.
And
our
muscles.
muscles.
Right, and your muscles. Those three things. And I want you to remember that now, because I'm going to now have you take a look at this coil that's in here. Here. You see right down in here how there's a coil, tiny wires coiled round and round and round?
Yeah,
see 'em?
there's an awful lot of them.
Thousands of turns, it looks like. Okay. Now, by turning this wheel, watch what happens to the coil.
Oh, you're turning the coil over.
See how you can spin the coil? In other words, we're getting the coil to move. Okay. Now let's apply some muscular force here and spin the coil and see if you can light the light bulb.
Nothing's happening.
Why not?
Well, I've got the muscle. Must be missing some. The magnetism. It's missing the magnetism.
Right. So we have the spinning coil, and we've got to spin it now in a magnetic field. Okay. Here are a bunch of magnets. Now, they're strong too.
They sure are.
Let's put two there. And two there. Okay, now give them a...
Boy, it's hard.
There, see
There
it?
we are.
Now, you see what you're doing now is you're changing your muscular power with the help of a magnetic force into light.
That's really something.
And notice that it was much harder to turn now?
Sure was. It was real hard.
In other words, in order to get some electricity out of here, in order to get enough electrons to flow, you have to work harder. If we put more magnets, we get a brighter light, but you'd have to work harder still, wouldn't you?
Sure would.
Okay, now this is the principle then of the generator. Have you ever heard that word, the generator?
Oh, they're in those big black things are in the powerhouses. But I've never seen them stand there cranking it. I mean, they don't crank it, do they?
No, they don't crank it. However, there are some types of generators that are cranked like this, but the big ones that you're talking about obviously don't have a crank in it. What is it they use to turn that handle back here?
Well,
Now, what was it you said about Niagara?
falling water.
If they get falling water now to hit the blades of a turbine or a paddle wheel, that would make it go around, and they connect the axle to this, and that would make this go around.
Oh, use the falling water on that.
What happens in the middle of the desert, though? No falling water.
Well, no electricity.
Well, actually, you supply some other kind of force. If you took coal and burned it so that you could get heat, you use the heat to change water to steam. The steam would then have pressure, and you could push that pressure against some paddle wheels or a turbine. That would make it spin, and you can connect the thing to here and make it spin. So you could use the energy of heat, changing water to steam.
Heat and falling water.
Yeah, in fact, heat is the major source of electricity in the United States. Most of the electricity we have around the house comes from heat. Well, so now we have two systems, both using magnetism, right?
Falling water.
One is gravity and falling water, yes, and the other one?
And the other is the steam,
Okay.
the heat.
Now, let us see if we can find a second system. Here. Get this out of the way. See this liquid here? See this,
Just a flat piece of wire.
looks like a flat piece of wire. Well, I'm going to put it in the liquid. Watch.
Oh, sure is bubbly.
Now, I put a flat piece of wire in there, right?
A long piece. It just disappeared.
Yes, it's gone.
That must be powerful stuff in there.
Well, it is powerful stuff in there. It's an acid.
Oh, no wonder.
Why do you say no wonder?
Well, from what I've heard, acid eats stuff up.
Yes. It just as it did this piece of metal, right?
Sure did.
So obviously there's some power in there, some energy available. Okay, now if we combine the right kinds of metals, like I have done here, copper and zinc, and put them in this acid, we can get electrons to move. In fact, watch. First, I want to add a little bit of this stuff, which helps the
Purple
system.
like
Yeah.
grapes. Starting to bubble again.
Okay. Now, do you want to hold on to that little motor? Because if I connect one side to one piece of metal, see?
Wow, we're making the motor move. Ooh,
Also getting a lot of gas from the top of it.
smells.
Obviously, we have a flow of electrons here in order to make that move, right?
Oh, we're taking the power from the acid and that,
Yeah.
and making the electrons flow and making the motor go.
Right. What we're doing, in effect, is using the power from the acid to act on a metal to push electrons around. Have you ever seen a thing like that before?
No, I don't believe I have.
Have you ever seen of that?
You mean a battery's got liquid in it?
Well, actually, a dry cell, that you ordinarily think of as being dry, actually has some liquid in it. It works on basically the same idea.
Oh.
So now, where do we use batteries around the house?
Oh, we use it in your flashlights and
Yeah.
radios. I've got a portable radio. And the cars, they have it.
And you use them as an auxiliary source of electricity when something happens to the regular source, don't you?
Mm-hmm.
So you see, now we're using a chemical action in order to push electrons through the wire. Now let's go back to our little bunch of balls over here so that you understand how we're using these forces in order to get electrons to move. Down here is a supply of electrons, right, in a copper wire. What is the force that we use now to pull that electron out of the copper and start it through
You're using your muscles now.
Yeah, I'm using my muscle now, but what do we really use when we want real electrons to flow?
Well, you can use falling water.
Right.
Or heat and chemical reactions.
Right. If you're going to use falling water or heat, what other kind of force do you combine with it?
Well,
What did you need? You needed your muscle, wire, and what was the third thing over there with the generator?
magnetism.
Right, magnetism. So here we have electricity, the flow of electrons. And notice we don't get something for nothing. That in order to get them to flow and do work, we have to use some kind of energy in the very beginning. And that the more current we want, the more energy we have to use, right?
Right.
Now this particular group of atoms represented copper atoms. And notice the electrons move through it rather easily. But what if we use some other kind of atoms? Could be other kinds. Some of them could flow easily, some of them with more difficulty. So now let's take a look at what happens when we send electrons through a wire where it doesn't go very easily. Let's try that. See this meter over here in the corner? See, what I'm going to do is bring current up here through this, over to through this wire, and finally over to this wire. So this is the important part that we want to watch. Now connected to this, I have a meter. You see what it says on the meter?
AC amperes.
Amperes. In other words, this is the amount of current. And we can measure the amount of current that's going through that wire by simply reading here on the meter a number. Now, let me turn it on and start putting current through that wire.
We've got 2 amperes, 3, 4.
Let's stop right there. What does it
5.
say? 5 amps. Okay. Now, let's turn it off because I don't want you to put your fingers around this wire when we have current going through it. What I want you to do is to look right down there. You see what I've written on that piece of wood?
1 amp, 6,000.
Well, never mind the thousands.
Wow.
Just 6.
So many of those zeros.
6280 followed by 3, 6, 9, 12, 15 zeros.
Boy, that's an awful lot of zeros.
In other words, here's what scientists have found out when they decided to measure the number of electrons that are flowing through the wire. In other words, if you had a counter and you were standing there counting click, 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 every electron that went by, you would find that it would 6.28, this is the way the scientist says it, 6.28 times 10 to the 18th. And that's that number down there. That's the number of electrons that would flow by a given point in a wire in 1 second.
Wow, that's an awful lot of electrons
Now,
in 1 second.
we had 5 amps, didn't we?
Oh.
So we'd have to multiply that number by 5.
Wow.
That would be the number of electrons that go by. You see now why it's considerable force? Because there's an awful lot of those things. Imagine that many balls rolling. Be considerable force, wouldn't it?
Sure would.
Okay, so this is now a current of 1 amp. Now, and that was a copper wire, just like the one we had, that we were pretending we had over there. A good conductor. Now let's try something else. Put a different kind of wire in. I'm going to leave everything else the same. I will now turn on the switch. We had how many amps before? 5?
We had 5.
Okay, I'll turn it on again. Now watch what happens. What do you read there?
It's 3. 3 amps.
In other words, we're missing 2 amps. In other words, we have the same amount of current coming up through here. Something happened over here because we only are reading 3 amps here. What happened to those other 2?
I don't know.
Well, does this make sense? Think of this. If the current, the electrons started to go up here, but they ran into resistance here, some kind of a friction that got in their way, then they wouldn't be able to get through and make the meter move, would they? Take this piece of paper down and touch that wire.
It's burning right through it.
Yes. Obviously
That must be hot.
The wire must be hot. Where did that heat come from?
Well, from the friction of the electrons coming.
Well,
That's why they don't all come through.
yes. Now, in other words, in order to try to go through, some of them couldn't get through, and their energy was changed into heat. And this is, of course, a very important principle. Where do we use a principle like this around the house?
Well,
Changing
stove.
electricity into heat. In a stove, where else?
Then there's the, well, most sockets. I mean, that's what you're using.
No, you're not using the heat from it.
Well,
Does your mother have a curling iron? No, probably not anymore. How about a waffle iron?
oh, she has
Yeah.
that. And then there's that stuff. She takes one of these big irons and she irons out the clothes.
Right. All because you can now change the energy of the electrons into heat. Right?
Right.
Now, we lost some current. We didn't have as much as we did before. Now let's try something else. I'm going to turn the current up even more. But in order to do this, I want you to turn out the lights. So get ready now, because I'm now going to... Okay, you go ahead and turn out the lights. Now, do you see what's happening?
Boy, it gets orange and starting to collapse.
And see, in spite of the fact that we've turned out the lights, notice you can still read what I put back there?
It's
See?
giving off light.
It's giving off light. That's the important thing. So now if you get these wires hot enough, you can eventually get it so hot that it'll begin to glow and give off light. And let me try this. Here, I'm going to set something else up here, and I'm going to turn that on just a little bit. Now watch. See this one glowing too?
Oh, it's
Just
a
like
light
this one over
bulb.
here? It's a light bulb. In fact, here, watch. I'll turn this one up as I turn the other one down. Now watch.
Oh, we can see ourselves.
See, you can see ourselves now, because though the energy from those electrons is now trying to push through that very hot wire, making it very hot and giving off a lot of light. So, of course, that's a very important principle, too, don't we? It's a good idea that we have electrons trying to get through wires, because light is very important to us. In fact, it's so important, I'd suggest you go turn it on.
Okay.
There. Because we got that filament to glow, we now have light. So, you see, while most people think of the idea that electrons flowing through a wire that you'd want it to flow through easily, it's important that they don't flow easily,
Some
because we
do,
can go
some
heat
don't.
and light from it. Very good. Well, now, let's try this. Make sure this is off. That one's on. That one's off, okay?
It must be hot.
It is. There. Now I'm going to turn it on again. And I'll turn it up before. What do we read on the meter?
Nothing now.
Nothing now. Why not?
Well, oh, there's when it goes up through here, there's nothing to carry it
Here,
across
keep
the other one
keep
and
your
come
fingers,
down.
keep your fingers noise in there. Let me turn it off again to make sure, as we talk about now. In other words, the electrons are now going to get up to here, but they can't go anyplace.
Place to go.
No place to go, because there's nothing for them to go across here. But now let's say that I increase the pressure. I turn it up higher and higher and higher and higher and higher. Pretty soon I get enough pressure for the electrons to go, in spite of the fact that there's no wire here, right through the air and jump over to here.
That's what the spark is.
That's right. That's what the spark is. When you get enough pressure, the electrons flow right through
Right,
the air
jump.
and jump across. So now let's go back and look at that spark. See if you can understand that. Here. Now, before I start it, I want you to understand what's happening. What I'm doing is taking relatively small current from this power pack here and running it over here to this transformer that now increases the pressure. We have a lot of pressure. So the spark can jump across a little tiny gap. Here, let me try it down here, and you'll see that there's a gap. See it?
Yeah.
There are two wires inside there, but there's no direct connection between them. When the electrons now come up through here, they have a lot of force. They finally jump from one wire to the other, and when they do that, they cause a tremendous amount of friction in the air with the molecules that they hit.
Oh, is
And
that
this-
why you can see it?
This is why you can see it. And of course, in some cases, by having a lot of pressure, you can make a spark this wide. In fact, I've seen sparks that'll jump the whole distance of this room
Oh,
by having enough pressure, see?
but why does it go up? I mean, it jumps across, but why
Well,
up?
here,
Why
let's
doesn't
try
it
it.
just stay
You get your
down?
fingers out of the way. All right,
Yeah, why not? Why does it go up?
now. Well, that's because I'm a mad scientist. You know, this is what mad scientists are always doing in the movies. You know, they have the spark that climbs up. Well, the explanation is really very simple. And scientists, you know, once you understand it, it's very, very easy. Think of this. When air is hot, it's easier for the electrons to get through because the molecules are further apart in the air.
Well, then it would follow the hot air.
Right. Hot air being a good conductor, this means that when you heat up the air with the spark itself, and the air starts to rise, the spark follows the air and goes up. When it gets up here, the spark gap is so wide, in other words, that pretty soon it can't jump across there anymore. Then it starts down here again, heats up the air, and follows the hot air going up. That's all there is to it.
Oh, it's quite simple. I mean, in the movies, these guys goes up.
Yeah, I know. And really, it's very simple. However, because this is a high voltage, don't get your fingers around it, so I'll turn it on if you want. And what they do, you see, they put it inside of a big tube, and then they have a couple of knobs on the end. They connect wires to it, and, you know, they nothing to do with the whole business at all. Then they have a big generator with lots of voltage down below, so they can get the spark to sputter off, and see, it looks real impressive. Really, it's not very useful at all. So now, you see the difference in the conductors. Air is not a conductor until you get enough force to go through. Now, when you first came in, I asked you what electricity was, and you had a little trouble. Think you can tell me now?
Well, electricity is the flow of electrons through a wire.
All right.
And some wire is better than the other. I mean, some will let it go, the electrons go through easier. And
how do we get the, what are the forces that we use to push the electrons through?
there was the falling water,
Which is gravity.
the
Okay.
heat,
Right.
and the chemical reaction.
Okay, now in the case of heat and falling water, what was the other force that we used to actually...
Magnetism.
Right, and magnetism actually did the pushing. So it wasn't so difficult, was it?
No.
Fine, well, when you go home now, you check with your father and your mother. I'll bet you they won't be able to tell you really what electricity is and how you get it started.
I'll have to try that out on
Okay,
them.
you try that out on them, because it's about time for you to be running along now.
Oh, but what are you going to do next week?
Well, next week we're going to do this up here, for instance. See this lamp? Well, I'm going to show you how you can make this yourself at home by getting a piece of paper and cutting it out. Here, let me turn the lamp on and get it started. There now. Now, maybe this doesn't make sense to you at the moment, but it will next week when this will help you understand what makes the wind blow, because we're going to investigate weather.
Be sure to be with us next week when Mr. Wizard and Betty Sue investigate weather. Watch Mr. Wizard was presented by the Public Affairs Department of the NBC Television Network in cooperation with New York University.